Hey, welcome back. In this video, we're going to see one of the most important applications of Taylor series representations. In this case right here, we're being asked to evaluate the integral from 0 to 1 of e to the negative x squared to an accuracy of at least 0.0001. This example is especially important for two reasons. First and foremost, e to the negative x squared is not just some crazy looking function that we like to play with, but it's actually essential to the analysis of probability and statistics. The e to the negative x squared is part of the expression for the normal curve. And second, importantly, is that e to the negative x squared does not have an elementary indefinite integral. And what that means is we can't actually write the antiderivative of e to the negative x squared using our functions that we have. Importantly to this statement, an elementary indefinite integral doesn't mean that it's like use like really basic numbers and expressions, but any function we've ever seen up to this point cannot be used as a representation for the antiderivative or the indefinite integral of e to the negative x squared. So what we're clearly going to do instead is use the power series representation of e to the x, compose it with negative x squared, and then we're going to integrate. Importantly, we're going to be left with this infinite series, and we'll have to remind ourselves of different properties we've had previously on how to get the accuracy that we need. So first things first, let's create the Taylor series representation of this function right here. And so it's going to be this e to the x right here. The only difference is going to be we're going to compose it here with the negative x squared. And so I'll just write that in right here. So negative x squared. And we can't forget to evaluate this divided by k factorial. My next work is just to make sure that I don't have any issue with my interval and convergence at all, but all x values that I could plug in here would land on the original interval of convergence, so we're just fine. Specifically from 0 to 1 is all I really care about in this case. One thing I'm going to do right here is just split apart the negative and then use some little exponent rules to clean this up real fast to make my life in the next step easier. So this is an alternating series that actually will be very important here soon. This is x to the 2k over k factorial. So now that I have this Taylor series representation of e to the negative x squared, I also remember that I'm allowed to integrate term by term. So the integral of e to the negative x squared is the same as the term by term integration of this statement right here. And so I'll rewrite this real fast. This negative 1 is just a constant term. It doesn't get affected by the integration. Here I'm going to add 1. So this becomes x to the 2k plus 1, and then divide that by 2k. So I'll write this as k factorial times this 2k plus 1. And again, just using the anti-power rule right there. Importantly, though, is I'm going to evaluate this from 0 to 1. And so what I need to do is take this and evaluate this from 0 to 1. I think one of the hardest parts about this application is that the notation just gets kind of mind-boggling. But remember, we're just going to evaluate this power series from these two values are all we care about. And actually, I can rewrite this statement right here. Because what this evaluation means is I'm going to take this series, which represents this function. So I'm going to take this series, and I'm first going to plug in a 1 here. If I plug in a 1 here for x, this is just going to be a factor of 1. So this whole thing simplifies into negative 1 to the k over k factorial times 2k plus 1. So that's that summation. And then minus when I plug in a 0 here. But if I plug in a 0 here for x, I have this factor of 0, and every term in this is going to go to 0. So plugging in 0 actually has no effect. So most simply is that this integral right here is represented by this series right here, again, because the minus 0 doesn't do anything. This is not a power series. This is a series that has just these coefficients or these terms described here. What we'll do next is expand this a little bit. So first step is when k is equal to 0, I'll get just a 1 on top for negative 1 to 0. I get 0 factorial times 2 times 0 plus 1. It's just times 1. So that's, again, 0 factorial is equal to 1. That's an important part there. When k is 1, that will be a -1. So I'll have this -1 here. And the denominator, that's 1 factorial. And then this will end up being 3. And then the next term will be when k is equal to 2. This will be positive, always a 1 on top. And then I have 2 factorial times 2 times 2 plus 1, which is 5. And then before I keep going with that analysis and write out more terms, I'm kind of lazy and don't want to do any more work than I need to. So what I'm going to do is figure out how many terms I'm going to need to have the accuracy that was requested. Important to this conversation is the fact that this is an alternating series. I won't go back and display the theorem that we know, but if you remember this conversation, I thought Julian did a really cool job in showing a visual of this alternation that goes on as you take these partial sums of any alternating series. The point being, if you're looking for how accurate is the nth partial sum, it's always as accurate as at least the next term. Importantly, this statement is only true for the alternating series. But again, I have this alternation right here because it's -1 to the k. But again, what I'm saying is if I am thinking of how accurate is it any partial sum, so stopping at any value right there, how do I know how accurate it is? The point is it's at least as accurate as the next value or the absolute value of the next value. And so what I'm going to do is look at the error in an nth term, meaning I'm going to take this expression for the terms of this series, and I'm going to plug in n plus 1 because I'm analyzing this term right here. So it's not a series anymore. It's just one term. So I have -1 to the n plus 1 over n plus 1 factorial times 2 times n plus 1 plus 1, and let's clean this up a little bit. Well, first and foremost, I didn't put my absolute values on here, and so that actually negates this part. The negative positive won't matter, and so I'm just going to have a 1 up there. And then down here, I have n plus 1 factorial, and then this would be 2n plus 2. So this is 2n plus 3 on this factor right here. And now actually I don't need these absolute values, specifically because there's nothing in this expression that would be negative. Again, the n is representing this iterative variable that starts at 0 and is positive. So neither this factorial or this factor could be negative. The question is when will this be less than or equal to 0.0001? And this might be a little unsatisfying if you've been following along for all of the rigor and the work that we're doing. But because of this factorial statement right here, there's actually no easy way to solve this using an algebraic way of solving it. So what I'm going to do is a numerical approach. I'm going to plug in values for n right here until I get out a value less than 0.0001. And after plugging in a few numbers, what I found is that when this is n equals 6, when this is n equals 6, this expression right here is 0.00001323. And to be honest, n equals 5 was really close. It was 0.0001 something, but just above 0.001. I had to go to n equals 6. So that means I need to calculate the first 6 terms. So to just finish this up, I've written these first 6 terms. Again, given this information, I know that I needed 6 terms to get the accuracy that I'm looking for. And important to note, and this can be really confusing as we go through all these properties with the k's and the n's, this s sub n is the first nth term. So I'm starting at 0 here. So my k is not going to 6, but you can see that I have 6 terms. That's what's being described by s sub n. But I've written these all out, and I'm not going to evaluate these by hand. I mean, I could, which is pretty amazing at this point, because most of these aren't too hard. That factorial is just 6. That'd be 1 over 42. But this becomes 120 times 11. I'm not going to do all that, but I did calculate it in my calculator, and what I got is that this value, actually I should say, is approximated by that, but this summation right here is equal to 0.74673, and I could write more decimal places, but actually even writing the 3 down seems a little superfluous because I've only guaranteed an accuracy for those first few 4 spots, or 2, 1/10,000th of accuracy. But this, again, without having an elementary integral, indefinite integral for e to the negative x squared, what I was able to do is rewrite this function right here with a Taylor series representation. It was important, and this will always be important, that my representation I'm using is on the interval, or the values that I'm using for this definite integral, I should say, or anywhere I'm evaluating this Taylor series at, is on my interval of convergence, which it was here in 0 and 1. Then, importantly, I have this power series, but this evaluation is more of just an arithmetic move, right? I'm plugging in values and evaluating. So I plug in a 1 for this expression right here. So this is just saying 1 plugged in here for x, minus 0 plugged in here for x, but every term would have a 0 as a factor, so that would be nothing. So then this definite integral is represented by this series right here. Looking for this accuracy was based on this property of the alternating series. That might not always be the case, but because it's an alternating series, it's a bit more easy to find this kind of accuracy. I found I needed 6 terms, so I expanded until I had my first 6 terms, feeling comfortable that this value right here is a dang good approximation, accurate up to 0.0001.